Alright, welcome to Polar Calculus Day 3. In this video we're actually going to get into the calculus on polar equations, so that should be pretty exciting. Okay, as always, calculus very often is about finding rates of change, and the most common rate of change that we have is dy dx, which tells us the slope of a curve. Now with polar equations, we're in terms of r and theta, not y and x. So finding dy dx is actually a process of finding dy d theta divided by dx d theta. So that way the d thetas cancel out, and we would have dy dx. And that's going to tell us the slope of a curve. So, if we had some sort of like cardioid, that's going to tell us what's the slope at this r theta value. So you can memorize this, but I think that's a little more complicated to memorize. It's much easier to first find y of theta and then y prime of theta, and then find x of theta and x prime of theta, and then use your dy d theta over dx d theta. So that's the approach that I'm going to take. If you don't like that approach, use this formula. I don't think it's a very easy one to memorize, but do what suits you best. But before we get into finding dy dx, let's find dr d theta and talk about that. So let's start with example 11. Identify and sketch the curve 1 plus 2 sine of theta. So because I'm familiar with these polar equations, I recognize that this is a limison, and it's either a dimpled limison or a limison with the curl, or the curve inside, and I notice that this value is greater because it's sine of theta. I know it's centered on the y-axis, and then finally, if I don't remember all these things, I can go to a calculator to help the calculator tell me that what I have is a dimpled limison. Not dimpled, a limison with the curl on the inside, or the loop on the inside. So there we go. And they are asking me to find what is dr d theta at 5 pi thirds. Well, this is pretty much straightforward calculations. R plus, oops, not plus, R equals 1 plus 2 sine theta. So if I'm finding dr d theta, I can take the derivative of both sides with respect to theta, and I get 2 cosine of theta. And then I want to evaluate that derivative at the value of theta equals 5 pi thirds. So 2 times cosine of 5 pi thirds equals 2 times 1/2, which is 1. Then if we were to assign some meaning to it, we need to figure out kind of where this is. 5 pi thirds, we trace along the curve, and when we hit the angle of 5 pi thirds, we're right about at this location, and the meaning of dr d theta at that spot is at theta equals 5 pi thirds, the radius is growing 1 unit per radian. So 1 unit per radian. So for every radian we gain, we're going to have a radius increase by a value of 1. So it tells us that the radius of the curve is moving away from the origin. Or not really away from the origin, but that it's increasing in value. The radius is growing, because at that point the radius is negative and it's becoming more positive. So there you have it, dr d theta. Okay, let's look at example 12. Example 12, identify and sketch the polar curve. I notice that with this curve we're cosine theta, so we're going to probably be centered on the x-axis, and I notice that my A and B value are the same, so that tells me it's a cardioid, and from there I can sketch my cardioid. We start out here at 4, and it comes in, does something kind of like that. Not bad. Again, you can turn to your calculator if you're trying to figure out how to sketch these if you haven't memorized them all yet. But we're asked to find dy dx. So the first thing I'm going to do is I'm going to find dy d theta. So what we have is y is equal to r sine theta. We know that. And we know that our radius is 2 plus 2 cosine of theta. So we can plug that in for radius and then times sine theta. So there's our y coordinate in terms of theta. And when we take the derivative of this, we will get dy d theta. And I apply the product rule here, and the derivative of the first is negative sine theta times sine theta. The derivative of the second is cosine theta. So we have radius times the derivative of the second. Okay, and we eventually are going to want to evaluate this at, looks like at pi halves, so I'm going to go ahead and do that now. Dy d theta at pi halves is equal to -2. All right, so we've got our dy d theta. Now we need to find dx d theta, and we're going to take the same approach. X is equal to r cosine of theta, and we can substitute our r value in there, 2 plus 2 cosine of theta times cosine theta. From there we can find our derivative with respect to theta, so dx d theta is equal to -2 sine theta times cosine theta, f prime g, plus f g prime. And finally, we wish to evaluate this at pi halves. So dx d theta at pi halves is equal to, plugging that in, we find that it is equal to -2 as well. So finally, we're looking to get our dy dx, and we know that is equal to dy d theta divided by dx d theta. And so we can plug in our values. Dy d theta is -2, and dx d theta is -2. So that simplifies down to 1. So that tells us at the angle pi halves, our slope is 1. And looking at the graph, pi halves occurs roughly at this spot, and if we were to draw a tangent line, we would get something that looks kind of like that, and that appears to have a slope of 1, which supports our findings that the slope should be positive at that point. Okay, example 13. Identify and sketch a graph of the polar curve, 2 minus 2 cosine theta. So first off, I see again that we're cosine and that our a and b values are the same, so I should be getting this cardioid shape, but this time we're negative, so it's on the negative half of the graph, and if I were to sketch the cardioid, I'm going to get something which looks roughly like that. All right, and we want to find the points in r and theta where we have vertical and horizontal tangent lines. So very quickly, just looking at the graph, If I'm looking for horizontal tangent lines, I'm probably going to have one there, and then if I'm looking for vertical tangent lines, I'll probably have one there, and there. So it looks like I probably am going to find 5 answers to this problem. And this takes up a fair amount of space, so let's zoom in here. And we're going to tackle our horizontal tangent lines first. And horizontal tangent lines are when dy d theta is equal to 0. And also dx d theta is not 0. So let's try to do that. First we write our y value. Y is 2 minus 2 cosine of theta times sine theta. And we're going to find our first derivative. So we're going to take the derivative of that with respect to with respect to theta, and we get y prime is equal to 2 sine theta times sine theta plus 2 minus 2 cosine theta times cosine of theta. So there's the product rule. And I'm going to try to set this equal to 0 so that I can find where it's equal to 0. So very first, let's clean things up. 2 sine squared theta plus 2 cosine of theta minus 2 cosine squared of theta. And when it comes to solving trig equations, it's easiest when you're working all in one trig function. So I'm going to take this sine squared and turn it into something in terms of cosine to match the others. So what I have is y prime is equal to 2 times 1 minus cosine squared of theta. If I go through the process of simplifying this down, I can distribute the 2 and I can combine like terms, and I wind up finding that y prime is 2 plus 2 cosine of theta minus 4 cosine squared of theta. And I want to set this equal to 0, because that would tell me where dy d theta is equal to 0. Okay, looks like I've got a quadratic in cosine. I can divide out a 2 and I can factor it. Divide out the 2 first. And then we'll factor this to cosine of theta plus 1 times cosine of theta minus 1 equals 0. And there we have a factored quadratic in terms of trig. First I ask, when does cosine of theta equal 1, and then when does cosine of theta equal negative 1/2, and I conclude that at the values of 0, 2 pi thirds, and 4 pi thirds, I get a trig expression that is equal to 0. Okay, the first part of this problem is done. It appears that we probably have horizontal at these points. We need to complete the second part to be absolutely certain that horizontal tangent lines occur at those points. And just looking at our graph, it looks like we should only have 2 horizontal tangent lines, and we found 3, so I suspect one of those is going to be ruled out as we move forward. Okay, so let's chase our vertical tangent lines now. And those are going to occur when dx d theta is equal to 0 and dy d theta is not equal to 0. So we need to find x and x prime. So x is radius times cosine of theta. And we find that x prime is 2 sine theta cosine theta plus. And then let's distribute 2 sine theta cosine theta minus 2 sine theta plus 2 sine theta cosine theta. Combine our like terms. 4 sine theta cosine theta minus 2 sine theta. And we're trying to set this equal to 0. So we're going to say 4 cosine theta sine theta minus 2 sine theta is equal to 0. We can factor, it looks like both have a sine theta in there, so we'll factor that, and they both have a 2. We'll factor a 2 out, and we get 2 cosine theta minus 1 on the inside. And we're going to then use the zero product property and find when does 2 sine theta equal 0 and when does 2 cosine theta minus 1 equal 0. And that concludes for us that theta is equal to either 0, pi, pi thirds, or 5 pi thirds. So there's 4 possible vertical tangent lines, and we just need to compare with what we've got. So looking at our graph, we see that there is 3, and we found 4. And the way we rule this out is we're going to look and see if there's any common values. And it looks like at 0, dy d theta is 0, and dx d theta is 0. So those do not count. We rule those out because we're getting that 0 divided by 0 error. And looking at the graph, that probably happens right at the origin, where we're getting this, this cusp. And cusps happen when we have dy dx equals 0 over 0, or cusps can happen. So there you have it. We found the theta coordinate for our horizontal tangent lines, and we found the theta coordinates for our vertical tangent lines. And we could stop here, except for the problem asks us to express it in terms of r theta. So here we go. Our horizontal tangent lines will occur at 2 pi thirds and at 4 pi thirds. If we plug those into our original radius equation, we get 2 minus 2 cosine of 2 pi thirds is 3. So our radius would be 3. And for the second one, our radius is, if we plug 4 pi thirds in, we get a radius of 3 as well. So looking at the graph, this looks like that would be at 2 pi thirds and at 4 pi thirds. And the radius at that spot is about 3 units. Finally, the vertical ones. Down here we'll write vertical. Those occur at pi, pi thirds, and 5 pi thirds. So we have 3 points that we need to find. First one is at pi. If we plug pi into the equation, we get 4. The next one occurs at pi thirds. And if we stick pi thirds into the equation, we get 1. And finally, the last one occurs at 5 pi thirds. and sticking 5 pi thirds into the original equation, we get a radius of 1. A lot of work there. Horizontal tangent lines sketched on the graph. Vertical tangent lines not yet sketched, but let's just take a look at this. A vertical tangent line at pi. I'm going to draw it over, repeat it over here. So at pi, our radius is 4. That's good for that vertical tangent line. At pi thirds, our radius is 1. That captures that vertical tangent line. And at 5 pi thirds, we get the other vertical tangent line. Woohoo! That is the longest type of problem that you will see in polar calculus right there. Finding, at least for me, finding the points of horizontal and vertical tangency in terms of r theta. So there you have it. All right, thanks for watching. After this video, you should be able to find dr d theta and tell me the meaning of that. And you should also be able to find dy dx, which is the same as dy d theta over dx d theta, and then be able to talk about the meaning of that. Helps us find horizontal and vertical tangent lines. Thanks for watching and enjoy your evening.